Okay, gentlemen. Today, welcome to the third online presentation from Lamah company. As maybe some of you know, we every month we are making this presentation for all our audience, for all consultants, contractors, who are interested in topics which is related to pumps and their controllers. In this month, we decided to discuss the topic of NPSH and cavitation, because we noticed there are many issues, or let me say confusion about these things in sites. For example, many people, they don't know exactly what the NPSH is and how we can have the benefit of knowing NPSH in things which is related to pumps. Sometimes it could be confusing some people. Is it related to the air inlet or not? Is it related to the suction lift of the pump? Many things, there is some confusion. This is one to clarify. And second, the problem which we call cavitation. What is this problem or this phenomena? How it starts and how we can control it, and even how we can predict if this will happen to us or not. So this is our trip for today. But before going and discuss this NPSH and cavitation, there are few things we need to remind ourselves about them. The basic things which is related to fluid mechanics that are related to these topics. Now, like some movies, sometimes, you know, some movies, they show you like short scene about the end, then they will come to the beginning of the story. This is what I will do today. Now, the end, we want to reach to this conclusion. Okay. What is the conclusion? To be safe of cavitation, you need to satisfy this condition, which is NPSHA, something called NPSHA, has to be bigger than NPSHR with safety margin. Now, what is the cavitation? What is the NPSHA? What is the NPSHR? What the safety margin what is the safety margin which we are looking for? These are 4 questions. We will answer it. But I'm just telling you the end of the story. It's remember that to be safe, to avoid cavitation, to be aware of the risk of cavitation, you need to make sure that the NPSH in your system is bigger than the NPSHR with safety margin. Okay? So this is what we will end up. Now, let us go to the beginning of the story. First, there is 2 things we need to clarify. There is something, we call it the absolute pressure, and there is other thing which we say it's the vapor pressure. Why we selected these 2 things specifically to remind ourselves about them? Because they are related directly for a suction pump and for the NPSH and the issue of cavitation. Now, absolute pressure. Guys, now, you know, when you have a pipeline and in this pipeline, you can have some gauges to read the pressure. This pressure reading this pressure reading, which you can see in your gauge, this is what we call gauge pressure. Okay? Gauge pressure. Gauge pressure, it's the pressure level that is shown on the gauge. This pressure shows the pressure of the water inside the pump, inside the pipe, excluding the atmospheric pressure, which means the atmospheric pressure, it's actually not included. It's not shown in the gauge. So, for example, if you have a tank and there is a pipe and you have water level here, up, let us say 10 meters of water. If you put your gauge here, you will notice the gauge shows 1 bar. Why 1 bar pressure? Because the column of water, 10 meters column of water, will generate a pressure of 1 bar. So your gauge will show, will give you an indication to 1 bar. But actually, if you want the reality, the pressure here is the 1 bar that is shown in the gauge plus the atmospheric pressure. Why? Because above this water, there is a long column of air. This column of air to the top of the sky creates a pressure which we call the atmospheric pressure. This atmospheric pressure equals to 1 atmospheric, which is 1 bar. So if you want the pressure on reality, here you will say I have 1 bar, this 1 bar, which is the gauge pressure, which came from the water column, plus 1 bar, which is the atmospheric pressure, equals to 2 bar. This 2 bar, this is what we call the absolute pressure. So the absolute pressure is the gauge pressure plus the atmospheric pressure. So here we can conclude a couple of things. The gauge pressure, once it shows 0, means there is no static pressure for the water. But maybe there is atmospheric pressure of 1 bar. But the gauges doesn't read the atmospheric pressure. Okay? The gauges doesn't read atmospheric pressure. Now, most of the times in pumping systems, we don't care about the atmospheric pressure. Why? Because, for example, if you have this tank and here a pipe, here a pump, and pump is delivering water to a higher tank. Here, you can see the atmospheric pressure here cancels out, encounters the effect of the atmospheric pressure from the other side. So you can see they are canceling their effects. So this is why we care about the pressure of the water as a static pressure only. Okay. Now, there is a question here. Once we say 1 bar equals to 10 meter head of H2O. How we knew that? How we come from this? Simply, you can make small experiment. If you brought a pipe, okay, closed from one of the endings, let us assume like this pipe. And let's assume this pipe has a length is 12 meter length. And fill it of water. Then bring this plate or whatever and fill it with water. And then flip this pipe and put it inside. What will happen? You can see the water will go down. Why? By gravity, right? By gravity. The water will fall down. It will fall down up to certain limit, then the water will stop. Why? Because when the water falls down, it falls down till we reach to the pressure of 0, which means we have a vacuum here. At the same time, we know there is the atmospheric pressure is pushing on the surface of the water. This atmospheric pressure, which is 1 bar. So we have 1 bar here and we have 0 here. So it stops. Once it stops, if we look to the elevation of the water, you will see 10.2 meter head of H2O. This is how we knew, because now we have a difference here. Here we have vacuum. So the water level, which goes up by the atmospheric pressure, which is 1 bar, leads to 10.2 meter elevation. This is how we knew that 1 bar will make a water column of 10.2 meter. If you change the liquid, this elevation will be changed depending on the density. Okay. So now, as a final conclusion, we have something called absolute pressure. Absolute pressure, it's the gauge pressure, the reading of the pressure, which you can see in the gauge, plus the atmospheric pressure. Now, let us go to the second term, which is the vapor pressure. Now, vapor pressure has a nice story. Let's start this story to define the temperature, or once we say, I have a hot water, what does the heat mean? Now, if you look here in this side, I can see it's just like a sample. Let us assume these circles are the molecules of water, H2O molecule. Because water, it's a liquid, so we know these molecules have some bonds between them. They are not strong enough to make this water solid. At the same time, they are not weak till the water becomes a vapor. It's in the moderate strength. But at the end, there is a link, bond, ties between these molecules. Now, once you give some heat, little heat, for these molecules, what will happen? Heat, once we say something hot, we know the heat, actually it's a kinetic energy. It's a movement of the molecules up and down in their place. Which means if anything becomes more hot, you can imagine the molecule will start to move faster. So, hot things means the molecule or molecules of these things is moving faster in their place. Now, for a water, for example, once we have these molecules, as we said, there is the bonds between these molecules. Once we start to heat the water, give it more heat. Once we reach to 100 Celsius, we know the water start to boil and evaporate, right? Why? Because once you heat the water till 100 Celsius, you can imagine how fast these molecules are. This will lead to break these bonds between the molecules. So these molecules become free and then they can escape, right? So heating molecules means we are generating movement in molecules. Once this moving becomes enough to break these bonds, then we can go from the liquid stage to the gas stage. Now, let us make another experiment also related to that. If you have a glass of water, like here, if you have a glass of water and it's open to the environment, you know, if you come next day, maybe you will find no water there, right? But you know, this water, nobody have drunk it, but you know, it was evaporated. But nobody heated. I mean, nobody put some flame to heat the water to be evaporated, right? But actually, this heat will come from the surroundings of the glass. And the molecules, the few molecules which can take the energy from the surroundings will break their bonds and they will go to the atmosphere. And so on. One by one, most of these molecules from the surface can take in some energy from the environment and they will disappear, right? They will evaporate. Slowly, after 2 or 3 days, all these molecules will go to the environment. Now, if I took the same glass, same water, but now we close it. What will happen? Also same thing, but there is a small difference. These molecules will take some heat from the surroundings and will evaporate. But because it is closed, they cannot go out. But these molecules, once they are evaporated and they are in this region, after certain short time, they will condensate. So they will go back for the liquid stage. But other molecules will evaporate. So it will continuously, there will be some molecules are evaporating and other molecules are condensating. okay, continuously, till they reach some balance. So you will see the water level is fixed and the amount of the vapor is also fixed, unless the temperature was changed. If we understand that, then we can go to other experiment. Let us go here. Look to this glass. We put some water here. And the temperature of this water is 20 Celsius. The temperature is how much? 20 Celsius. Now, we will close this glass from the top and we will mount here a pressure gauge. Okay? This is a pressure gauge. Now, I will not heat. I will not do anything. I will put it like as it is, and the temperature is fixed 20 Celsius. After a while, when you look to the pressure gauge, you will see it's not showing to 0. It shows, it gives you a reading of 0.0234 bar, which means it's 0.23 meter head. This is the reading which you will find here. But you will ask yourself, why, how this pressure was generated? I didn't heat the water, and the water has 20 Celsius. How this pressure comes? Simply, this water took the energy, because we know we have 20 Celsius, so there is some content of energy, and some of these molecules on the surface of the water will evaporate. Once they are evaporating, they will create some pressure inside here because they cannot go outside. Again, some of them will condensate, some of them will evaporate, and so on until they will reach to the balance. This balance, we will see the pressure is 0.023 bar. Now we brought some flame here and we started to heat. We heated, give heat for the water, heat more, the temperature becomes increasing till we reached 50 Celsius. Once we reached the water 50 Celsius, we will maintain this temperature. And after a while, when we look again to the pressure gauge, we will see the pressure is fixed and higher amount. It shows the pressure is 0.1234 bar, which is 1.23 meter head. So the pressure increases. Why? Because we heated the water, so more molecules become evaporated, so they will make higher pressure in this area. Now, we will again increase the flame. We want to heat the water till it reaches 60 Celsius. After a while of fixing this temperature, you will see the pressure becomes 0.19, which is 1.99 meter head. See, the temperature increases. Now, heat again more up to 80 Celsius. As you can see, it's almost close to half bar. It's 0.463 bar. And once we heat it up to 100 Celsius, you will see the water actually starts to boil, and you'll see these hot bubbles inside moving, and you will see the pressure in the gauge shows 1.01 bar. Now, this pressure, which is generated here, this is what we call the vapor pressure. This is the vapor pressure. Okay. Now, the vapor pressure, it's actually a like aspect for each liquid. I mean, each liquid has different vapor pressure, which means if I brought an oil and I heat it till 60 Celsius, that doesn't mean the pressure also will be like water 0.19 bar. It will give you another different thing because this is different from type to type of liquids. Okay, but this is what we call the vapor pressure. Now, we want to understand more about vapor pressure and how we can boil liquids. How can we evaporate liquids? Now, maybe someone will tell me the water boils at once the temperature of the water becomes 100 Celsius. This is, we all know that if we heat the water till reaches 100 Celsius, it will start to boil and molecules will evaporate. But actually, this is not the root of the case. This is not the root. The root is, gentlemen, the liquid will boil and evaporate once the vapor pressure of the liquid reaches to the same level of the pressure which is on the surface of that liquid. For example, once the vapor pressure of the water equals the atmospheric pressure on the surface, then the boil will happen, regardless the temperature. Regardless the temperature, gentlemen. This is why, again, here, do you remember when we said, if you heat the water till it reaches 100 Celsius, the vapor pressure will be 1 bar? This 1 bar equals to 1 bar of what? Of the atmospheric pressure. So the boiling actually will happen when the atmospheric pressure or the pressure, total pressure on the top of the surface of the water equals the vapor pressure of that liquid. In this moment, the boiling and evaporation will happen. Now, somebody will tell me, if this is correct, that means we can evaporate the water under 20 Celsius. And this assumption is correct. How? Let us say if I brought a glass of water and the water is 20 Celsius. It's cold, right? Now, if we closed the surroundings and air is inside, then I will bring some vacuum pump and start to evacuate the air inside. The pressure on the top of the water will start to decrease because I'm removing the air. Will decrease. Once the pressure of the air inside that place reaches to 0.023 bar, you will see the water is actually boiling and evaporating, even the water is 20 Celsius temperature. Why? Because that means, let me say, if you can boil the water in two ways. One way, it's to heat the water to increase the vapor pressure till it becomes to the same level of the pressure at the surface, which is the atmospheric pressure, for example, if it's open to the area. This is one way. And the second way, instead of heating the water, no, we will decrease the pressure on the surface till it reaches to the level of vapor pressure. In both ways, you can evaporate the water. If you evaporate the water by adding heat, this evaporation which will happen, we call it hot evaporation. But if you evaporate it without temperature, this is what we call the cold evaporation. In our topic today, the NPSH and cavitation, we are afraid of the cold evaporation more than the hot evaporation. Our pain will come from the cold evaporation. This is why we describe this. This is why we need to know the vapor pressure and to know that we can boil water and evaporate it in low temperature. How? By decreasing the temperature, by decreasing the pressure on the surface of the water. If we decrease it, if we decrease the pressure on the surface of the water to the level of vapor pressure, your water will evaporate and will generate bubbles. Okay? Now, last thing to add as an introduction, how the pump sucks water which is below pump's level. As you can see here in the water level which we suck is lower than the pump level, right? How the water moves from down to the top, how this is happening? Simply, the water, it's not the source or the, let me say, the, it doesn't have the potential to bring the water from down to top. But who pushes actually the water to flow from down to top, there has to be some force, but the force comes from the atmospheric pressure. How? First, to start a pump and make and let the pump to suck water, before operating the pump, you have to make something called priming. You have to make priming. How we can make priming? First, you have to put here a non-return valve or foot valve. This is one thing. Second, you have to fill the suction line with water. Even the pump itself has to be filled with water. If you made this, then we can tell you made priming for the pump. So priming, it's putting this non-return valve, filling water in the suction pipe and the pump itself. This is the priming process. Once you finish the priming process, then you are ready to start up the pump and start pumping. Now, the mechanism, how it is, once you start up the pump and start to rotate suddenly, very quickly, the impeller rotates quickly. The impeller will push the water inside the pump. It will kick it suddenly to the discharge line. In this moment, there is an instantaneous vacuum will happen. It will not, there will be no vacuum, clear, but instantaneous vacuum will happen inside the pump. So the pressure inside the pump becomes zero instantaneously, okay? This is inside the pump. But for the water here, in the surface of the water here in the tank, we have atmospheric pressure. And this atmospheric pressure equals to 1 bar, which is 10.2 meter head. So, as you can see, for the water, here there is absolute pressure. Again, absolute. Why we said absolute? Because we included the atmospheric pressure. So, the pressure here, absolute pressure is 10.2 meter, right? But inside the pump, the absolute pressure instantaneously is zero. So we can see here, we have delta P, we have differential pressure now. We have 10 meter head here from the atmospheric pressure, and we have zero inside the pump, so we have delta P. This delta P, this is the force which makes the water to continue flowing from down to the top to reach the pump. Okay? So, now, gentlemen, if you made some opening in the casing, immediately you will see the pump will start pumping. It will work, but there is no water coming inside. Why? Because the atmospheric pressure will come here, so this delta P will disappear. There is 10, it will become 10 meter head here, 10 meter head, so we have no differential, so the pump will stop, the pump will stop sucking. Okay? So this is how the pump makes suction of water, especially from down to top. Now, these three things which we said, absolute pressure, vapor pressure, and how pump is sucking water from down to top, these things, if we understand it, we can now mix them in our minds and we can conclude many things to understand better and to know what is the NPSH. For this process, please follow with me answering the couple of questions. First question, question number one. Question number one. As you can see here, we have in this example, it's just an example. We have a pump which will suck water from down. Now, this example says the elevation between the water level, water surface, and the pump level, it's 3 meters. Also, they are saying in this example, assume that the friction or the head loss caused by friction inside the suction line is equal to 1.2 meter head. Yes, gentlemen, this lecture is recorded. So you are most welcome. Tomorrow you can ask us and we will send you the link of the record so you can see this lecture again. So don't be afraid if you lost something, okay? Now, back to our example. The elevation, we said we have 3 meters and the friction loss is assumed to be 1.2 meter head. and the temperature of the water is 25 Celsius. Now, question number 1 to us: how much of absolute pressure? Again, see, absolute pressure. I'm asking about absolute, okay? How much of absolute pressure will remain at the pump inlet, which means here, at the pump inlet? I'm asking about the how much is the absolute pressure for the water when it reaches the entrance of the pump. It will not inside the pump, at the entrance. To answer this question, you will tell me, I know the water here, the absolute pressure of the water here is 10.2 meter head, which comes from the atmospheric pressure, right? So as a startup, I know I have 10.2 meter head from the atmospheric pressure. Then, to know how much it will remain at the pump, that means I have to subtract the elevation, because to push the water to go up by 3 meters, this is not for free. You have to pay for it. You will pay 3 meters of this atmospheric pressure which you did, right? So you will subtract 3 meters from the atmosphere, right? So 10.2 meters atmospheric pressure, there is minus 3 meters because of the elevation, to overcome the elevation, minus 1.2 to overcome or to compensate what we lost because of the friction inside the suction line. 10.2 minus 3 minus 1.2, this will equal to 6 meters head. That means I know now the absolute pressure of the water on the water at the inlet of the pump is 6 meters. Okay, it's 6 meters. So this is the answer of question number 1. Now, question number 2. Question number 2. How far is the remaining absolute pressure higher than the vapor pressure at the inlet pressure, pump? You said the answer of question number 1, we knew that the absolute pressure here at the pump inlet is 6 meters. Now, we want to know how much is the difference between the remaining absolute pressure at the pump inlet and the vapor pressure level. Vapor pressure level. Why I'm asking about this? Why we care about this difference? Because you remember when we said about the boiling and the evaporation, what we said? We said this evaporation will, and boiling and evaporation generating bubbles will happen if the pressure on the water surface equals to the vapor pressure. We are afraid of this scenario. We are afraid the scenario when the absolute pressure on the water equals to the vapor, because the water will start to boil and create bubbles. We don't want this. This is something, if happened, related to problem called cavitation, which we will describe after a while. Okay, so we don't want this happen. We want to make sure always that the pressure above the water surface is higher than the vapor pressure by some extent. This is why I'm asking this question number 2. So we want to know this remaining absolute pressure at the pump inlet. I want to know how much it's higher than the vapor pressure, because I need actually for this pressure to be higher than vapor pressure. But how much it has to be higher? This is what I'm asking you. What you will tell me, your answer will be that I know now the remaining absolute pressure at the pump inlet is 6 meters. The vapor pressure, you can use this scale, which you can see at the extreme right. This is specific for water, okay? You cannot use for everything. This is only for H2O. If you know the water temperature, you can know how much is the vapor pressure of the water. Now, in this example, the water temperature is 25 Celsius. So 25 Celsius, it's here, between 20 and 30, right? So 25 Celsius means the vapor pressure converted to the head, this is in meter head, is 0.3, almost 0.3 meter head. So again, you have 6 meter absolute pressure remaining at the pump inlet, and you have 0.3, this is the vapor pressure. So now you can calculate the difference between them. So the answer for the question number 2 is 6 meters minus 0.3 meter equals to 5.7 meter. 5.7 meter is the answer for question number 2. Look here, what happened? This 5.7 meter, gentlemen, 5.7 meter, which is the answer for question number 2 in this example, this is exactly what we call NPSHA. So the NPSHA, what is it? The NPSHA is the difference between the remaining absolute pressure at pump inlet and the vapor pressure. This difference between the absolute pressure and vapor pressure, this is the NPSHA. Okay? Now, NPSHA, N from net, P from positive, S from suction, and H from head. Why we call it net positive suction head? Because I'm asking and looking for the remaining absolute pressure, which is the net absolute pressure. Okay? Now positive, why positive? Because I want to know this remaining absolute pressure, how much is higher than the vapor pressure? How much is higher in positive side than the vapor pressure? Suction, because this is related to the suction side of the pump, and head, because I'm talking about head, not pressure. Okay, what about the A, small? This A small comes from the word available. Why? Because as you can see, this NPSH, which we calculated, it's actually related to the suction line, not to the pump. This is something which is available in front of the pump. the pump didn't make it. So it's available for the pump, but the pump didn't make it. This is the NPSHA. NPSHA, it's the net positive suction head that is available in the system for the pump. And this NPSHA has to be calculated. How? By using this equation. Actually, this equation, it's the conclusion of the previous questions which we made. You remember question number 1, we were asking about the remaining absolute pressure at pump inlet. Then we asked about how far is it from the vapor pressure. If we combine these two questions, question number 1 and number 2, we can get one equation, which is here. NPSHA, it is the absolute, it's the atmospheric pressure, which is 10.2 meters, plus other head sources. Sometimes there could be some other head sources, like what? In this example, or in any place when we suck from down to top, when I have suction left, here I have no other sources of head. Usually it's only the atmospheric pressure. But suppose if I put here a submersible pump and I wanted to calculate the NPSHA for the pump which is on the top. In this way, I have to say I have 10.2 meter head atmospheric plus the head which is generated by the submersible pump. This is what I mean by other head sources. Any head sources has to be added to the atmospheric pressure. Okay? So again, back to this equation. So NPSHA is the atmospheric pressure plus other head sources minus the elevation if it's negative suction. If you have negative suction, then you have to subtract the elevation. But if you have positive suction, then you have to add the elevation. Negative suction, guys, if I have tank and pump on the top, this is negative suction. The elevation, it's here. This is the elevation. So in such case, I will deduct the amount of the elevation from the atmospheric pressure. But if I have positive suction like this, as you can see, the pump is next to the tank. In this situation, this elevation, which is the water level, because as you can see, the water level is higher than the pump, this elevation will be added to the atmospheric pressure. Okay? Now, again, so atmospheric pressure plus other head sources minus elevation if it's negative pressure, or plus elevation if it's positive suction, minus friction. Friction is always has to be subtract, minus the friction, minus the vapor head, the vapor pressure converted to head. If you made this, you will get the NPSHA, the available in your network. So back to our statement, which we said at the beginning of our session today. To be safe of cavitation, which we will describe later, you have to make sure that your NPSHA is bigger than something called NPSHR with a safety margin. Now, you know the first thing. Now you can know what's the NPSHA and how to calculate it. What about the NPSHR? What is the NPSHR? NPSHR, R comes from the word called required. Required by whom? Required by the pump. Actually, NPSHR is the minimum NPSHA acceptable for the pump. NPSHR is the minimum NPSHA that could be accepted by the pump. This is the NPSHR. Okay, how can I know the NPSHR? How I can find it? I cannot calculate it, but the manufacturer of the pump, he's the one who has to tell me. How he can tell me? Simply, you will go to the performance curves of your pump. Usually, the pumps has 4 main types of curves. There is the curve of head HQ curve, which is the head and flow. And there is a curve efficiency with the flow. And there is power with the flow. And there is NPSHR with the flow. So I can now find the NPSHR by going to the last curve, which you can see here. This is the NPSHR. Even if they didn't mention R, you know it's the NPSH required by the pump. As you can see, this curve generally is almost flat for the lower side of flow rate up to the best efficiency. After that, you will see the NPSHR will start to be increasing by increasing the flow rate. It will be increasing in very clear way. So now in this example, for example, at 11 cubic meter per hour, you can see the NPSHR is almost 3 meters. NPSHR is 3 meters. Now, all pump manufacturers are telling us, all of them, they agreed that this value of the NPSH, which you get from the catalog, they are saying, please add half to up to 1 meter head as a safety margin. Why? Because this curve is general in the catalog. It's general. The manufacturer actually, they are producing thousands and thousands of models for, of the same model, thousands quantities of the same model. Impossible they have this, will have the same curve, because at the end during production, there is some very minor differences, difference in roughness, you know, they cannot be 100% the same. Also, the instruments that we are using, there has some, you know, accuracy level. So this is why they are telling us, please, this the NPSHR, which we will get from our curves, put 0.5 to up to 1 meter head as a safety margin. So now you know the NPSHR, how to find it. And this safety margin, which we said 0.5 to 1 meter head as a safety margin. So now you know NPSHA, NPSHR with a safety margin. So I can tell you, if your NPSHA is higher than NPSHR, including the safety margin, then you are safe. You are aware of the risk of cavitation. So this is what, now you know what is the NPSHA, what is the NPSHR. Now, let us talk about the cavitation. First, as you can see here in front of us, there is a pump and there is a flow inside the suction line. The pressure, the absolute pressure here has some certain amount. When the flow moves inside, flows inside the suction line, there is friction, there is elevation, whatever, we will see that the absolute pressure actually goes down. When we reach the inlet of the pump here, the pressure, we will see the absolute pressure drops from certain level up to here. So here we reach the inlet of the pressure, inlet of the pump. This is the vapor pressure level. So as you can see, I have some difference between the absolute pressure that is remaining at the pump inlet and the vapor pressure. This is the calculated NPSH, which is the NPSHA as we described before. Now, the water goes inside the pump. When it goes inside the pump, the port size becomes smaller in diameter. Then when it goes to the impeller inlet has also smaller diameter. Once you decrease the diameter, the flow will, the liquid velocity, the velocity of the liquid will increase. But when the velocity will increase, this absolute pressure will go down. We want to make sure that this pressure will go down further, go down inside the impeller. It will continue going down up to certain limit. It will go down to the maximum. We want to make sure this maximum, once we decrease the absolute, or once this absolute pressure is decreased inside the pump, whatever it decreases, it should be always above the vapor pressure level. Okay? Then the absolute pressure will start to increase. Why? Because the effect of the impeller and the volute, so the pump is pressurizing the liquid, right? But the point here, we have to make sure that whatever this absolute pressure goes down, it should be always above the vapor pressure level to avoid this cold evaporation and boiling and generating bubbles. Okay? Now, if the pressure, absolute pressure goes down and it reaches the inlet pressure, the pump inlet with low amount, even if it's higher than vapor pressure, as you can see here, the absolute pressure is still at the pump inlet, it's still above the vapor pressure, right? but with small gap. I mean, the gap between the absolute pressure and the vapor pressure at the pump inlet is small. We know the water goes inside the pump, the absolute pressure will continue going down. It will be decreased. Unfortunately, if it decreases till we reach the evaporation level, the vapor pressure of the water, in this situation, here inside the impeller, the water will start to evaporate, generate bubbles. This is what we call the cold evaporation. So here the impeller is rotating, and this is the vanes. You can see here the yellow bubbles. These yellow bubbles are vapor bubbles. How they are generated, how they came. As we said, because the absolute pressure of the water goes down till it reaches the vapor pressure of the water. So cold evaporation will happen. These bubbles, vapor bubbles, will be generated here. But these bubbles will not stay in the same place because, you know, the impeller is rotating. So by centrifugal force, this bubble will continue going. But once they reach this place, in this place, the pressure of the water will start to increase by the effect of the impeller. So once the pressure again increases, this vapor pressure will disappear suddenly. Why they will disappear? Again, these vapor bubbles, they are not air. It's not like air. They are vapor bubbles found because the pressure, absolute pressure comes to the level of the vapor pressure. But once the pressure goes, the absolute pressure on the water goes back to higher level, these bubbles, the source of presence for these bubbles is gone. These bubbles will disappear. Once they disappear, they will leave a vacuum bubbles. Disappear, and the vacuum will be in their place. But this vacuum will disappear immediately. But how? This is the problem. This is the vapor bubble. As you can see, this is the vapor bubble. This vapor bubble is surrounded by water. But once the pressure, the absolute pressure goes back high of this water, as we said, this bubble will disappear. But how it will disappear? It will collapse, quickly collapse. So the surrounding water will go inside this bubble to occupy this gap, which is left by this vapor bubbles. So the water will flow quickly, very fast to fill this gap. The speed of this water, which want to fill this gap equals the speed of sound in water. The speed of sound. This is just to imagine how fast it is. It's very fast. And once it goes to fill this gap very fast, this water will hit to each other. You know, it's like this. The water will come from all directions and will meet in the middle. They will hit. This hitting of the water, which is by a speed of sound, they will hit and they will generate two things. They will generate a wave of pressure, very tough wave of pressure, and this wave will be reflected to the other parts of the pump, plus they will generate a jet of water flowing so fast in this speed of the sound, and they will hit the surface of the impeller here. It's very tough bunch. It's very tough. If you see these pictures, you can imagine how tough is this water. It's like a hammer. It's very tough. You can see these metallic impellers. See these holes in the impeller veins? See, these are holes, and then it becomes very clear crack. Look, the loss of material for this impeller. It's very dramatic. And by the way, this to happen, it will not take long time. I mean, this is not an impeller after 5 years. It depends on how long this cavitation continues. But if it's continuous, this could happen within few weeks or months. It's not long time, gentlemen, because some studies I heard, they are estimating the strength of this water jet around 10,000 bar. This is why when cavitation happens in a pump, if you come closer to it, you will hear some very strong sounds. It's similar like stones hitting a steel. You will think for a while that there is some small stones inside the pump and they are hitting the pump. But once you open the pump, there is nothing inside. There is absolutely no stones. Actually, it's just vapor bubbles collapsing suddenly, and water goes by speed of sound to occupy this space which is left by these bubbles, and they hit the surface of the impeller. This is the generating of these bubbles and then collapsing. This is what we call the cavitation. So cavitation, it's the process where the absolute pressure on the liquid goes to the level of the vapor pressure. So vapor bubbles will be created, and once they collapse, this is the process of cavitation. This is exactly what is the cavitation. Bubbles and collapse. Now this cavitation, when it happens, it makes very tough, harmful effects. One of them is what you can see here, this damage in the impeller. But there is also other bad effects. Like what? The pump itself will vibrate. And this vibration also will go through the pipes to the system. The head and flow of the pump will decrease. you will notice the head and flow are lower than supposed to be. The power is higher. That means also the efficiency of the pump goes down. You can, if you ignore that, later you will see the bearings could be affected, the shaft and mechanical seal. So you can see this cavitation, once it happens, how bad is it for the pump? Impeller, shaft, mechanical seal, and bearings, system, all these things will be affected. The problem, you know, these bubbles, once they are created, they are in millions. The number of these bubbles are in millions, and the lifetime of these bubbles is around 0.2 seconds, which is very fast, a lot and very fast. Pop, 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 pop. Now you can understand what is the cavitation and why we are afraid of the cavitation. Why we need, during pump to selection, to make these calculations of NPSH to make sure we will not face this cavitation. Now, if cavitation happens, let us come to a practical part. If I saw a pump facing a cavitation, how can I solve this problem? Simply look to this slide. Any strategy you will choose, there are many ways to solve your cavitation issue. Any strategy that leads to increase the NPSHA is helping you to avoid cavitation. Any strategy decreases the NPSHR is helpful to avoid the cavitation. So, how can I increase the NPSHA? You can increase NPSHA, for example, if you have negative suction, try to this elevation to make it less, which means make the elevation between the pump and the water surface lower. Because lowering or decreasing the elevation means higher NPSHA, right? Also, look to the sources of friction. Try to minimize the friction. Sometimes this friction becomes high because of a strainer at the section side. There is a strainer, and this strainer, there is many dirt stuck in it, and people ignore it. They didn't clean the strainer. So once the strainer is close to be clogged, it generates very high friction. This friction decreases the NPSHA. So the solution is, please clean the strainer. Sometimes, maybe, if the pipe is 2 inches, maybe you can make it 2.5 or 3 inches. This will decrease the friction. This is different from case to case. Each case, you want to see what is the major factor that is lowering the NPSHA, so you will think how to increase it. Sometimes in some industrial applications, we try to cool the water so the vapor head comes lower. This is also a possibility. Sometimes maybe none of these things could be helpful. So then you can think about how to add other head sources that that can support the atmospheric pressure. Like what? Like putting pump here at the inlet of the suction. So this is also a solution. Now, maybe someone will ask how I can decrease the NPSHR. For the same pump, for example, if your pump is working here, this is suction, this is pump, this is discharge, and there is a valve here. So if your pump is working here, and you noticed cavitation, one of the solutions is to make throttling by closing partially the valve at the discharge side, so the flow rate will go less. So you will decrease the flow rate. Once you decrease the flow rate, you can see the NPSHR goes down. But if you have the chance to change the pump, you can look for another pump that has lower NPSHR. Or sometimes I can, instead of having one big pump, I can use two smaller pumps in parallel, because the smaller pumps will have lower NPSHR than the big one. This is also a solution. Using VFD, because we know if we decrease the speed of the pump, the head will be, the pump will be decreased, right? The flow will be decreased. Also, the NPSHR will be decreased if you decrease the speed of the pump. How much it will be decreased? The square, the percentage of the increase or decrease the speed, which means NPSHR, the initial one, over the NPSHR, the modified one, the changed one, equals to the RPM, the initial, on the RPM, which you will get after using the VFD squared. So also, VFD can help you by lowering the speed to eliminate or to finish this problem of cavitation. Now, there is one question. If I have a closed loop, this is the pump, you know, and the water is just circulating, and the water fills the piping completely. In this situation, there is no atmospheric pressure, right? There is no atmospheric pressure. But what I have the pressure of the water column. So this elevation, this water column will generate the pressure instead of the atmospheric pressure. So I have other head sources, which is the water column. Okay. And which is the same as elevation, which means here the elevation and the head sources are together, and they are the water column. Okay, so you will say the water column or the static pressure, which is created by the water column, minus the friction, minus the vapor head. Okay? This is how you can calculate the NPSHA in a closed system. Okay, if I added a pressurization unit to make pressurization to the system, then you will say the pressure of this pressurization unit plus the water column minus the friction loss minus the vapor pressure. This is how you will calculate the NPSHA for a closed system. Okay? So, up to here, I can say we finished our presentation for this month. You are, of course, most welcome to ask any questions. And by the way, gentlemen, this is me, Engineer Omar Nimr. I'm the Sales and Marketing Manager for Lamah Company. And this is my WhatsApp number. You are free to call me at any time or send me any of your questions about this topic or any topic related to the pump or problem you are facing with pumps or control panels. I will be very happy to answer you. And you can, if anybody has questions, you can ask me. Most welcome, Muhammad. Thank you so much. And thank you for everybody, for all of you, and for your patience to hear this presentation, especially it comes after your duty work, duty time. So hopefully to see you next month with a new presentation with different topic. So in June, inshallah, we will meet again. From now to that time, I wish all of you a pleasant time with your families and have a nice day, all of you. Thank you so much and bye-bye. Thank you, Farouk. Thank you.